All right, let's get started. Good afternoon, everyone, and welcome to the EOL seminar. It is my pleasure to introduce our speaker today, Dr. Jason Kelley from the University of Utah and Department of Water Resources, conducting flux research at multiple sites throughout the Pacific Northwest. Previously, Jason was employed for 2 years as a research engineer at the Water Management Unit of USDA's Agricultural Research Service in Parlier, California, and for 3 years as an assistant professor and in the Department of Soil and Water Systems at the University of Idaho. Jason received his PhD in Water Resources Engineering at Oregon State University in 2016 and was supported by the USDA NEFA Fellowship during his postdoctoral research. At the University of Idaho, Dr. Kelley studies crop water requirements, consumptive water use, evapotranspiration, and environmental thermodynamics, with a specialization in eddy-covariance technique of flux measurements using machine learning methods to integrate complex environmental data. In his spare time, Jason enjoys building guitars, working on farm projects, and dreaming up new sensors. Jason's seminar today will re-examine simplifying assumptions and measurement techniques in the era of flux networks. For those participating virtually, welcome, and you're welcome to ask your questions to Jason in the Slido window at the bottom of the presentation screen, and we're going to have a Q&A session at the end of Dr. Kelley's seminar. Dr. Jason Kelley, welcome, and the podium is yours.
Thank you. All right, so as I've warned a few people, I fly through slides because I always pack way too much into these talks. So if I start to see distressed looks on faces, I'll try to slow down and maybe some sacrifice at the end. So I was asked, I think the theme I was given was present something about what I think is compelling research ideas in the field of flux research right now. With that introduction, gives a pretty good summary. I've worked over most of the Western United States, I thought I'd start with a slide of the last time I was in Colorado, which is amazing to me, but that was 10 years ago, putting up an eddy flux tower between Rifle and Silt, so over by Grand Junction. So I thought it was fun to have a picture from Colorado. And this work is supported, I'll talk about this again at the end, but my previous position, Agricultural Research Service, so that was all appropriated dollars, supported a lot of this research, and then the remainder of this research is supported by the University of Idaho and a few other research institutions. And I'm a member of a working group for the FluxNet co-op, and so hopefully I'll be able to represent well kind of the questions that I've been trying to get the community to think about. Okay, so I'm going to start off. I try to get all my slides with a lot of words on them out at the beginning. I thought it'd be good to start with terminology. I'm not sure what everybody uses for terminology, but a lot of the terms that I'm going to be using in this talk, they'll be defined differently by different people. And I want to just make it clear at the outset what I'm talking about with these specific terms. So the majority of this talk is about reconciling gaps or non-closure in the surface energy budget. So if I'm measuring the four simple components of the surface energy budget, being net radiation, sensible and latent heat flux, which are typically measured with turbulent measurement techniques, and soil heat flux, or the change in soil storage. I'm referring to a closed budget, and that's the surface energy budget. The available energy is part of that. The available energy is the source term, so the net radiation minus the energy that's abstracted as heat stored in the soil. The turbulent flux is a combination of the sensible and latent heat fluxes. The residual of those measured values, I'll have it written in a number of ways in my different slides, but it's typically RES or residual, and sometimes I normalize that residual by the source term, so the net radiation, or sometimes I just shrink that down to the shortwave, the downwelling shortwave radiation. Then I also talk a lot about ET, or evapotranspiration, which is the combination of evaporation and transpiration from plants. And there's two different kinds of evapotranspiration I'll be talking about today. I've got actual evapotranspiration and reference or potential evapotranspiration. And I'm going to talk a little bit about what defines those. So I want to talk about the simplifying assumptions that are commonly shared amongst the measurement community and the modeling community that often are unspoken or not always formulated in the same way by different modelers or by different practitioners. And so I wanted to start with this. There are actually two foundational papers that I think are really inspiring and lay out some of these simplifying assumptions. So I'm not going to go into a lot of detail about this paper, but Ira Bowen's dissertation is one I always tell grad students when they're worried about having a sufficient research for their dissertation. I point to his dissertation, which was 13 pages of handwritten text. It's a fabulous, coherent argument that underlies a lot of the work that I do and a lot of the work that defines flux measurement at the surface. So Bowen essentially took a ratio and came up with some first quantitative estimates of this ratio by deriving three different cases, which were essentially boundary conditions. And from that, calculated the Bowen ratio, which is the ratio of the sensible to latent heat flux. He was able to show that could be calculated from a gradient. So the idea here is that we're equating flux with diffusion, that turbulent mixing can be equated with a diffusion and associated with a diffusion coefficient. And so there are a couple of assumptions that were important in this paper that have been carried on forward. So one is that the energy that is received at the surface is partitioned between sensible and latent heat flux, and that in the cases that Bowen was looking at, he's talking about conduction and evaporation, meaning sensible and latent heat fluxes from a water surface. And that, by definition, includes evaporation as a significant piece of that partitioning. And also that there's similarity between those diffusivity coefficients. And that diffusion, and so what I'm saying is that the diffusion is the model for turbulent mixing. And diffusion is a steady process, whereas turbulent mixing is not a steady process. And that assumption is one of the ones that I want to look at today. So the second paper that has similar assumptions is Penman's 1948 paper, which has been the basis for a lot of additional engineering work over the years, coming up with calibrations for different kinds of nonlinear parameters about how evaporation is controlled from the surface. And the trick in Penman's paper and the Penman equation, and that's a somewhat familiar form of an evaporation equation, where you're calculating the latent heat using the Clausius-Clapeyron relation, and he did a nice trick in this paper where he, instead of needing to measure gradients, he's using temperature and humidity measured at one height, and then using the Clausius-Clapeyron equation to think about the slope of the saturation curve and measuring a vapor pressure deficit. So without going into the proof for that, the other part of this that was really important was that there's been this unknown wind function. And that unknown wind function was something that Penman and others had posited. And different authors have done different things with this to come up with essentially a way of parameterizing nonlinear behaviors like somewhat like a diffusion effect, but where you have wind that's transporting trace gases and like water vapor from the surface as a function of the vapor pressure deficit or gradients. And so built into this Penman equation is an assumption that the surface energy budget is closed and that all of these non-linear behaviors can be parameterized typically through resistance terms in the standardized equations for reference ET. And that the other critical piece to this to make that trick in this paper work was that we're talking about evaporation from a well-watered surface. So it's from water, from soil, or from a crop, but that ET or that evapotranspiration or the latent heat loss is coming from a well-watered surface. So how this plays out in terms of the rollout of networks. So flux measurement networks that have been built by engineers for decades now have, at least in the world of evapotranspiration and estimating water requirements from natural surfaces, have been structured essentially like this. So we have the typical meteorological measurements. The part of this station, this measurement and monitoring station, that is often left out of the description is the reference surface. And I can guarantee you, if you travel around the West and look at monitoring stations for agricultural water management or ET monitoring, that reference surface is not a reference surface. It's quite often just desert or the side of the road or a ditch or an airport. And that assumption requires a lot of bias correction. So the networks look like this. These networks are building weather stations. There are a bunch of them throughout the West and actually throughout the country now and throughout the world. And they're measuring a standardized reference ET. And that standardized reference ET is reported on a daily basis typically. And that reference ET can then be used with different calibration factors for growing different crops to estimate what is the water requirement for these different crops. But from the role of the meteorologist or the Bureau of Reclamation or whoever is the institution that is operating and maintaining these stations, they need this standardized methodology so that they're reporting a value that can be used with the sets of coefficients that have been developed for specific applications. So stepping forward into kind of the things that are being done now, I actually came expecting everyone had already heard of this, and this website is the product of a NASA project that's been going on for about 6 or 7 years now. And they are producing rasterized data sets using Landsat images for, at this point, almost the entire continental United States. And they can run the models that are behind this interface to give a 30-meter pixel size report of now daily evapotranspiration and other environmental parameters. But in terms of flux measurement, they're giving what's known as an actual ET value, not a reference ET value, but an actual ET value. And they're doing that through a combination of data sources. They have the Landsat thermal images, and they're also using some other map information about what's actually out there on the landscape. And then they're also combining that with ground-based measurements from these reference ET stations. And then the last kind of network that sort of ties all these things together is I wanted to talk about Ameriflux, and Ameriflux is, amongst other global networks, one of the organizations that tries to tie together PIs from around the world, and in this case around the Americas, who are doing flux measurements to get at actual ET values or other trace gas transport. So carbon monitoring is a big emphasis. There's also, Ameriflux also has a group working on methane fluxes and nitrous fluxes. And so the goal of this kind of network is to come up with a standardized technique for doing quality control on data and also bring PIs together to pool resources, training, and data provisioning so that the work of flux science is being having the maximum impact, but also that there is some measure of reliability in the data. I took it out. I did have a slide in here that showed all the Colorado Ameriflux sites, and they're within 50 miles of here. There's at least 6, I think. So, yeah, this is a community effort. PIs work together, and then there's a support system there that helps with the data processing, the physical infrastructure and training. And that's much like what I gathered the mission of NCAR is. So, okay, so what have I been doing with this? So I'm going to start with what I was doing a few years ago, a number of years ago now, at the end of my PhD and into my postdoc work. I was kind of put forward as the sacrificial postdoc to work on machine learning in the research group I was working with. And the idea was that we could use machine learning to try to reconcile these different methodologies. We've got a way of measuring reference ET, we've got ways of measuring actual ET using direct measurements like eddy-covariance measurements. essentially we have these really widely distributed networks of relatively low quality data that's very difficult to maintain, but has a long history and a lot of sites. And then on the other side, we have researchers who are doing maybe short deployments because the complexity of the methods that they're using are hard to support for long periods of time. And the idea of this project was, how can we reconcile these two? Can we use high quality flux data to train or inform these network systems to output something that's useful to end users? So this is really geared towards not necessarily producing research quality data, but using research quality data to inform management decisions and the kinds of information that was generally available to the public. So we worked on this for a few years on a bunch of different sites. There's one of my flux measurement sites at the edge of a center pivot there, irrigating a really terrible bean crop. And there were all the normal challenges. One of the great things that came out of working with this very difficult field was that I got a huge variability in the water use efficiency. There was a huge variability in the flux. There was so much soil evaporation, and there were so many weeds, and there were so many problems. I got a huge range of conditions, and that was great for training my machine learning, my neural networks. They got to see every kind of condition under the sun. In subsequent work, what we've seen is that when I train these weather stations to report actual ET, using the sort of a training data set like eddy-covariance, what I found is that the training is really sensitive, not so much to the number of sensors or how good my measurements are, but to the range of conditions that they experience in the field. That the true variability, the environmental variability, was the determining factor of how much information density was contained that the machine learning algorithm could pull out. Because what I'm doing with machine learning is essentially a very naive approach. It's really just a multilinear regression or multi-nonlinear regression solver. And but what's happening at least in the agricultural engineering community is, while there's a lot of interest in using machine learning, there aren't typically robust parameters that are being reported that allow an end user to say, yeah, this training is good, or this methodology is good, or this is how many sensors I need. And so one of the things we've been working on is coming up with some easy to understand statistics, some simple statistics that really relate the robustness of that kind of machine learning approach and allow it to translate between how good is a weather station that's operated by a county agency and how good are the data that come in from a researcher, and how can we reconcile those two? All right, so changing gears a little bit. One of the observations that we were making over and over again at these flux measurement sites and this goes back to what I was talking about with Penman and Bowen. I was noticing over and over again that there seemed to be, I look at the time series of the fluxes, and I look at the time series of the residual of that closed energy budget, because I'm measuring all four components, measuring net radiation, measuring sensible and latent heat flux using eddy covariance, and I'm measuring or modeling essentially the soil heat flux. And I was seeing that the residual, the extra energy that wasn't being measured, that's a known problem, that we under-measure the turbulent fluxes. But the closure of that budget seemed to be correlated with the aridity, or how much actual evapotranspiration divided by how much potential evapotranspiration or reference evapotranspiration. So there can be lots of reference evapotranspiration. If it's hot and dry, any water out there is going to evaporate. But if there's no water to evaporate, the actual evapotranspiration can be quite low. So when you look at a crop or any surface in the landscape, when it's wet, you can have a lot of evaporation. But just because it gets hot and dry, and particularly in the West, where our primary productivity season is offset from when we receive most of our rainfall and precipitation, we get these wide swings in the ratio of actual to precipitation, actual to potential evapotranspiration. And so I'm calling that aridity. And when actual evapotranspiration is 100% of potential evapotranspiration, or the evaporative demand, then that ratio is 1. And on the vertical axis here, what I'm showing in this case, and bear with me because I do switch these axes a couple times in the presentation, but we go from 0 to above 1, and essentially when that ratio is at 1, we've got 1 minus the residual. And so this is when we're at 1, we have complete closure. The surface energy budget is closed. When we are at 0, we've lost it all. And when we're above 1, we're measuring some extra turbulent flux from somewhere, and we're not sure where. And what we were seeing over and over again was this correlation in time. They'd water the crop, and there would be good closure. We'd be getting excellent closure, like on the order of 100%, which is sort of unheard of. And then that crop would dry down, and we would have every indication that we were just not measuring any of the flux. We would be getting down to 20% closure at times, which is just unacceptable. Typically, for these kinds of eddy covariance measurements, the general rule is that the undermeasurement of flux by skilled operators between 10 and 15%. And there are a number of mechanisms that has been attributed to, but generally it's been accepted that around 20% is the bar below which the data quality has suffered for some reason of measurement error. So I've got those brackets. I've actually got a plus and minus 20% on here to just show kind of the range of how much of our data were falling outside of this curve when the field dried down. And we hadn't done anything different with our field measurements. It's just that the conditions in the field had changed. So I was seeing this over and over again in different kinds of landscapes. That prior one was that picture of the field growing the snap beans where it had lots of problems. This was actually a regulatory let's see, which one is this? Oh no, I'm sorry. That one's vineyards. This one is the irrigated bush beans. And so what I had there was that the irrigator was not irrigating on a regular schedule. So I had periods of time where the beans would basically completely dry out, and they were very drought stressed. And that's where we have those red markers. And then looks like and then the blue markers indicate this relationship. So we have this bimodal behavior where we have closure that seems to be related to field conditions, but not really any clear mechanism for why that might be. And then we saw it again with irrigated alfalfa, and this was a supported project for that NASA OpenET project. And we were getting, there were a bunch of scientists working on this, an excellent field site with great maintenance, and we were still getting this kind of, this very predictable behavior where we were having this closure seemed to be related to how much of the water demand was being met. And then we had, in this case though, it also broke down by how many days between harvests, how many days had elapsed since harvest. So as that canopy of that alfalfa had grown back in, we got that very standard behavior. But immediately after harvest, there was that relationship really broke down. Okay, so what I did with this is that I designed a field experiment where we set up 4 eddy covariance systems. There were multiple objectives for this project, one of which was to look at footprint analysis. So typically you wouldn't mount an eddy covariance sensor so low to the ground. And I was trying to look at, if we measure the Bowen ratio and we measure the sensible and latent heat flux in somewhat challenging or difficult conditions because of stability conditions or other environmental conditions that impair the typical QA/QC procedures for the flux measurement. If we can pair that and look at these measurements in these 2 adjacent but very different conditions, are we going to see those same behaviors, and is there a height dependence for this? And so I'm measuring the eddy covariance at 2 heights, one of which is way too low and one is more of a standard height above a crop. And then I'm also measuring the Bowen ratio with gradients. So I'm measuring temperature and humidity at 3 or 4 heights on each of these towers. And these are only located a few hundred meters apart. But so these were patch trials down in California. The fallow area, the fallow field there, had not received any rain or irrigation for over 2 years, and there was 0% water content from the surface to 6 feet deep. It was as fallow gets. There was no water in that field whatsoever. And so this is in the Central Valley of California. Been several years of drought. So what were we seeing? Well, the first thing I wanted to check was, okay, I've got the green markers showing the measurements taken over the alfalfa, and the gold markers are showing the measurements taken over the fallow field. And I wanted to look at a relationship with this aridity index, this ratio of actual to reference evapotranspiration. and the bone ratio. So the bone, they should coincide. If there's very low, so the bone ratio again is it's the ratio of sensible to latent heat flux, but it's also the ratio of the gradient of temperature, the vertical gradient of temperature and the vertical gradient of humidity or vapor pressure. And so as it gets drier and drier, because the denominator of that ratio goes to zero, the function becomes somewhat unbounded. And so what we see here over several orders of magnitude, we see a relatively stable bone ratio over the alfalfa where there was water being applied. And then we see a completely unstable bone ratio in the dry field. All right, so when we think about results, again, and this is where I flipped the axis, so bear with me. 0 here indicates no residual, no error. So when we have 0, we have a closed energy budget on the vertical axis. And these box plots describe, the bin numbers are different for each box, but essentially there's at least several hundred 30-minute samples in each of these bins. And so what I'm looking for are trends across a range of aridity values in these two different treatments. And I'm looking to see if I can identify, are we getting that bimodal behavior? Do we have a certain kind of condition that happens with the alfalfa and the well-watered crop, the well-watered surface, and a different set of modal behaviors in the fallow field? Knowing that there's other error compiled into this. So there's other errors that are due to advection and due to measurement error and due to sensitivity limits of the sensors. Do we see these modal behaviors? And what I was finding was that the sensor in the fallow field really always fell, the residual always fell. We basically were able to take a fairly high quality measurement, even though there was no ET. There was no latent flux. There are some errors in that. You can see that the residual actually exceeds, so it's negative in this case. So the turbulent fluxes exceeded the amount of energy that was received from net radiation. But in general, you don't see that wide distribution. You see a similar behavior across that range of aridity. The sensor over the alfalfa, though, strongly showed that change in modal behavior as you go from well-watered conditions on the right and then move up the plot to the left. You see that the error actually exceeds the radiation measurement. So the majority of cases are in those central conditions where the aridity index is 20% to, say, 70% of the potential of evapotranspiration. But there is definitely that modal behavior. So how did the bone ratios compare? Well, again, the bone ratio is completely unbounded on those right two trials with the fallow field. On the left, what we have are two plots that compare the gradient bone ratio measured by gradients measuring temperature and humidity at two heights. That's the x-axis, the horizontal axis. And the vertical axis is the bone ratio estimated the way that it's typically used for calibrating remote sensing data or using eddy-covariance data, where the bone ratio is a ratio of the sensible and latent heat flux measured by the turbulent exchange using eddy-covariance. And as I suspected, they were different. I had seen this before. They're different, and there's definitely a bias where the gradient bone ratio is stronger. And so I tried different combinations of measuring the bone ratio with that eddy-covariance sensor at a low height and an upper height, and using different combinations of the gradients measured at different heights. But essentially what I saw was that this bias was consistent, and then it just added noise to use any other combination than the ones that I used here. So the question is, does it make a difference? So the bone ratio is used to solve those standardized reference ET equations, and all of the energy balance methods that are used by remote sensing, and also the QA/QC procedures that are used in flux measurement, all depend on the idea of preserving a bone ratio and forcing closure of the residual budget. So if there's a relationship between these two, is this difference in how the bone ratio is measured going to then influence the subsequent flux calculations from these two methods? So the short answer is no. It wasn't that clear. As in most environmental studies, I found, okay, the historic methods worked pretty well, and the new technology-heavy methods also worked pretty well, and they gave slightly different answers. There are certain periods which I can't really explain why there were differences, but I've got the circle blue markers and the triangular green markers indicate the Bowen ratio and the eddy covariance respectively. And in general, the trends that we see day to day, so this is total ET, or latent heat flux multiplied times the latent heat of evaporation. If we take that ET from those two methods, the trends follow. There's, and there was a lot of skepticism that I could use a thermal hygrometer, that I could use basically off-the-shelf components and just calculate a Bowen ratio, but I found that it works quite well in this instance and in other instances as well. So the takeaway for me was, okay, we can use the Bowen ratio and we can use it in parallel with flux measurement, maybe use machine learning to do some parameterization. But essentially what I saw was that these two methodologies, there is, even though the base of the assumptions that go into them about what is the Bowen ratio, what is the ratio of sensible to latent heat flux, and how is flux gradient similarity, how does that create some bounds around when it's possible to take robust measurements of flux? What I found was that the two methods overlapped well within the sensitivity that's required for this kind of daily estimate of total water losses or total water demand from crops. So while that may not be true over shorter time periods, and it may not be true to detect specific instances if we were looking at momentum flux or something more specific about intermittent effects, or it is enough to help us schedule irrigation or make water management decisions, all of which really occur using data from a daily time step and no finer. Okay, so going back a little bit into thinking about residuals and the closure of the surface energy budget, this is a more typical presentation you would see in a publication about eddy covariance data quality, and where you're comparing the available energy on the x-axis and your independent variable on the y-axis is the turbulent flux, the combination of sensible and latent heat flux. And really the reported statistic would be something like an ordinary least squares, just an r squared, and the slope of the regression line through those. And so that's pretty typical presentation that I would need to do for a normal publication and describe the quality of the flux data that I had measured. But what I was finding was that if I took those regressions over subsets of the data, if I looked at, in this case of alfalfa, how many days had elapsed since harvest, I again saw that closure. I saw the linear, the slope of the regression line would change. The pitch of that line would change according to the conditions. And I did this for a bunch of different conditions, some for how much time had elapsed since irrigation. I had done it for the antecedent soil moisture. I did it for the soil moisture at the time of the flux measurement. Did a bunch of different parameter spaces. The main ones that really jumped out were how much crop, how much above ground biomass was there, and how much water, or how recently had water been applied to the surface. So, and then the other piece that we really got out of this, and I'm not going to go into a lot more detail with that analysis, but the other thing that we saw was that neither the Bowen ratio nor the surface energy budget residual calculated on 30-minute intervals, it's not constant. We often treat these kinds of descriptions about the forcing mechanisms or the error statistics as something that can be averaged over a specific time period. But often that throws away the time component of our data. And so by calculating the residual in every 30-minute period, and instead of treating that as a bulk statistic or a normalized statistic, I am plotting this, in a box plots over the course of a day. So those are the days or hours of the day on the x-axis, and showing how the energy. What this is really saying is that energy is stored somewhere in the system. Over the course of the day, we're under measuring turbulent flux over the course of the day, and that energy is being stored somewhere in that system. Now that might be outside of our control volume, it might be because of advection, it might be because of mismatch between our sensors, But there is some reconciliation. That budget does spring back over the course of a 24-hour period as energy is released from the soil, as energy is released from the storage terms because of essentially the water, which has a very high thermal capacity. And the amount of water affects the modality of this. So one of the things I've done with this using long-term, short-term memory neural networks is to try to replicate those time-varying processes and look at lagged correlations in the different components of the surface energy budget. And then when I apply those neural networks and try to predict what different components of the surface energy budget, different component measurements, so different components of the net radiation, the sensible flux, latent heat flux, and especially the soil heat flux, how can we model those storage terms as partial differential equations without having to come up with an analytical solution for the partial differential equation? Instead, use the sort of a data-heavy, a mechanism agnostic approach to get at, well, what are the time-varying processes and how do those vary in time themselves? So this would sort of be like wavelet analysis. We know that there's a function here, and we know there's a time scale associated with it, but that time scale changes in time. And so rather than try to solve double derivatives, I'm just using the model to learn, okay, what is the behavior? How can you replicate that? How is it a function of the different environmental parameters that I'm measuring? Feed that into it, and then output that as a change in the residual. And so on the top histogram there, I'm showing these 3 different surface treatments and how much residual we're finding at different error levels, and then how that shifts when we model those same fluxes, in this case, the soil heat flux. And again, somewhat inconclusive, but definitely a different mechanism, and there's some tricks to how these machine learning models were trained. But anyway, that's a publication that's hopefully forthcoming soon. So I've got a few minutes. I'm just going to run through a couple of other results and different kinds of field trials that I've done. So following those alfalfa field trials, I tried something similar using the Bowen ratio and eddy covariance to see if there were some simple ways to use these methods to get out, to essentially to use the Bowen ratio and relatively low-cost instrumentation to get at the ET, the water demand for different crops that, and this is one of the real challenges in agronomic water management. Flux measurements can tell you what the research stations said that crop needed for water in 1980 when they did a study using a lysimeter, but that doesn't tell you anything if the farmer decides to prune their trees a different way, or if they are actually shorting the crop on water because they don't have enough water supply. So these kinds of questions about real stressors in the environment provide a whole source of research opportunities, but a lot of unknowns about how do we parameterize these reference ET equations, or how do we measure actual ET so that we can get at the demand side and apply the amount of water that's actually required to maintain yields. So that's been the majority of my work for the last bunch of years. And I was setting up instrumentation like this in different kinds of, so we've got hazelnuts in northern Oregon on the top, and in the bottom, trellised citrus, which is a relatively new development by a couple of companies in the San Joaquin Valley. And I don't have time to actually show many of the results. The Bowen ratio is actually very helpful in calculating ET at a much lower cost than using eddy covariance. But some of the interesting things I've been trying to do with this is to reformulate how we describe the data quality and the quality control methods, and also the error or uncertainty that's reported with these data. And so closure, is typically estimated using ordinary least squares, giving an R squared value and a slope of a regression line. But I've been looking at it like, well, we're really talking about an energy budget, and you wouldn't balance your checkbook with an R squared. You would be balancing your checkbook by just doing a sequential tabulation and summation. And so what I've got here is a running filter where I'm totaling that energy budget over 30-minute periods, and then over typically, like in this case, I think I'm using a 7-day period where how much energy has been accumulated day and night from all those different components of the flux measurement. And what I've done here is I've combined different instruments. So I've got soil heat flux measurements in an area that gets a lot of sun, or on top of a berm, or deep underneath a berm. And I've got a net radiometer that's seeing mostly crop, or I've got another net radiometer that's seeing mostly alleys between the crops. And then I'm combining these with the turbulent flux measurements that I took to see how close to each of these different combinations of sensors come to reporting a closed energy budget. Quite often what happens is that on the heterogeneous landscape, the experiment prescribes however many sensors you can afford. If you can afford 2 soil heat flux plates, you put out 2. You put 1 in the shade and 1 under the crop. And then you do some kind of aerial weighting where you say, okay, well, 80% of the crop is, out there, 80% of the crop is, so we're going to say 80% of the heat flux data measured in the shade of the crop is our correct, combination of these 2 data sources. But what I'm saying is that, well, I don't know which one's right. I put a bunch of sensors and there could be a gopher under there. There could be all sorts of things going on. And so can I combine these in different ways to get a way of, can I combine my sensor information in a way that allows me to interpret which of these are actually a robust representation of that heterogeneous landscape that I'm measuring? Oh, I guess I did leave one in. So I've got the eddy covariance and the Bowen ratio here. Kind of out of time. There's a couple things I want to hit here at the end. So so I've gotten the methods to work pretty well. Good enough for my irrigators. They're really excited. Operationally, what we're aiming for is coming up with these cumulative water use. And so this is where daily aggregation is really sufficient for a lot of the practical applications. The big interest right now in a lot of the Western states, from especially states' departments of water resources and irrigation coalitions and the SGMA mandated reporting down in California with groundwater management, they want to know what the ET is everywhere. They don't want to know what your eddy covariance tower or even your reference ET station says. They want to know what the ET is everywhere for every field, every day of the year. And this project, the Open ET project, is basically delivering a data product that reports on a field basis and also on a pixel basis, the ET for every day of the year, going back 20 years. Well, they haven't quite released it all, but going back at least 6 years for every field and actually all the areas of the Western United States, from Texas west. And there's a lot of questions. Is this correct? How correct is it? What's the uncertainty associated with this? And so a lot of my work, and what I'm going to fly through here in the last few minutes, is how can we validate this? They have a ground validation campaign using basically eddy covariance towers, but there are lots of different approaches to doing these kinds of reconciliations. And so a lot of the work we're doing, like in this case, we were looking at citrus production in the San Joaquin Valley and looking at the variability across the fields. And those color codings indicate the amount of ET, cumulative ET over a month of time. And we had stations kind of in the central part of this map. And what I was trying to get to, and probably relevant to the kind of ongoing research aspects of this, is how can we reconcile all these different methods? So we have reference ET methods with crop coefficients that we know are out of date but are good approximations and are often better than what the irrigators are currently using anyway. We have soil sensors that tell us what the soil water storage is. We have flow meters that tell us how much water they think they're applying. We have a couple of different methods for getting the actual ET directly. And we also have these new satellite models. So what I'm trying to do is try to reconcile these. Each of these methods requires calibration. Everything requires calibration, and everything has some measure of uncertainty. So my goal is to really look at physical mechanisms, and can we tie together these different, use models to tie together these different measurement methods to come to some physical explanation for why uncertainty or calibration would be applied to one data set in one way. Not just that we calibrated our sensor and we're going to apply a regression coefficient to adjust our electrical signal, but that our calibration corresponds to some observation that we were able to make in the field, and that when we make observations of different sensors by different methods, that those two numbers can line up based on some kind of physical mechanism. Pretty much out of time. So I'm working with NASA and with Department of Water Resources in Idaho to look at irrigation efficiency, but also just flux measurement for water resources management. So we're using footprint models and these remote sensing data and doing field-based measurements. So this is a barley field in Kimberly, or no, in the Magic Valley and of Idaho. And what we're trying to get, what I'm doing for these reports is generating footprint models where I come up with a percent attribution of the turbulent flux. So I'm using Clune's model to estimate how much of that flux, how much of the measurement can be attributed to the irrigated area, and how much of that flux measurement should probably be attributed to outside the flux area. So when the wind blows from different directions, that flux footprint is that flux is measured from air parcels that are being transported from different areas of the landscape. And the reality in the real world is that the wind blows from different directions. So we're trying to tie together these flux footprint models with uncertainty, and also with the remote sensing measurements taken both within and without the field. So can we see behaviors that are observed within and without the field, and then tie those daily measurements to the where we think that measurement was representing, what part of the field or outside the field that flux measurement was representing. And in this case, we've got the plus markers indicate the remote sensing models inside the field. The X markers are outside the field, and then we have our flux measurements, the circle markers, bouncing around between the two, which sort of corresponds to the kind of common sense notion that if you have a sensor that measures the wind and you have it on the edge of the field, it's going to measure sometimes inside the field and sometimes outside the field. So that gives confidence. There are other parameterization issues that we've got to work through in terms of how the remote sensing models work. But this is where we're going with some of the research that we're proposing to do for the next few years. So that's it. I have a whole bunch more slides that are all hidden. So, I mean, if people have questions, I might have a slide to answer your question. But these were this is support different grants and projects that I worked under that supported this project. And yeah, this was a great team that we did an experiment during the 2017 eclipse, and had a whole network of eddy-covariance stations out trying to measure the turbulence decay spectra when the eclipse turned off the source terms. So we turned off the net radiation, we turned off the downwelling radiation, and then measured, did we, during that 2 minutes of darkness, did we see the atmosphere respond? It was really fun. And then the other thing that was really fun was that we were able to look at sort of the ergodic assumption and using ensemble averaging with that big array of eddy-covariance sensors. So yeah, fun stuff. So there's some great people in this picture. I don't have time to name them, but I really like working with the team, and I think that's really the only way we get this kind of science done. So thinking about the assumptions that are baked into these methods and how network information, network data are being used to inform some of these remote sensing models, I think is really, that's the compelling area of research and flux measurement that I'm working on. And yeah, with that, I'd be happy to take questions. So thank you for your attention.
Well, thank you for a great presentation and for keeping well within time, which means that we have plenty of time for questions. And Fletcher is going to monitor the questions that come into Slido. So do we have any questions in the audience?
Thanks. That was great, Jason. So in your comparison with eddy-covariance measurements and the Bowen ratio efforts, your results, just curious what you think your results say about the relationship between, or the assumptions about scalar diffusivity similarity, and how it's controlled by your aridity index. Like, well, how does the aridity index modulate that relationship, I guess?
Well, I mean, I'll leave it to better scientists to talk about diffusivity coefficients, because that's, I mean, there is an analytical approach to trying to get at the robustness of a diffusivity coefficient, and there's a long history of engineers doing work that didn't always agree, and I don't think I'm well informed enough to speak about diffusivity coefficients and similarity theory about those specifically. The things I have observed, though, is that well, two things. One, there's a temporal aspect to it. So there's that time diurnal and time variability of the gradients is really important. And that's true at every scale, of boundary layers, from near surface up to synoptic scales. And that that spatial component, the height of the gradient. When I was first interested in building Bowen ratio stations, one of my advisors said to me, well, here's the rule. You know the rule for how big your fetch has to be for a weather station. Here's the rule for a Bowen ratio station. If your ratio between the top of the vegetation height or the roughness height and the bottom sensor, that distance has to be 1/4 or of the ratio between the two sensors. It was a real rough guess. And he said, sometimes it's going to have to be more, and sometimes you can't really get away with less. And what I was finding by, and I've done maybe a dozen of these experiments where I put temperature and humidity sensors at a bunch of different heights, is the steepness of the gradients at the bottom is what creates a divergence term in the flux measurement, and also it really intersects quickly with the sensitivity of the ability to measure a gradient. I'm not using chilled mirror hygrometers. I'm not using a very sophisticated method to measure the vapor pressure. I'm using an EE181 HMP, or I'm using a HMP 60. I mean, they have big uncertainty bounds. So that identifying tying that sensitivity of the gradients with the separation, and also tying it with the time variability and the sensor response time, I think is really important. And then the other part is that I have to calibrate my sensors both for temperature, even brand new off the shelf sensors. I'm calibrating them for temperature and humidity in sets, both against a dew point generator. But I'm just in a forced air circulation chamber just to get sets where I know these two sensors have been exposed to the same conditions in the same airflow, so that I can say something more about the robustness. And when I started doing those calibrations, my gradient Bowen ratio calculations went from not making any sense at all to corresponding to eddy covariance measurements. So sensor sensitivity is a big piece. Knowing how close you have to be to the surface before it becomes impractical, because there's dirt and water getting up on your sensors all the time, because those gradients are very steep near the surface. And then knowing your averaging period, I'll do things like, a lot of the data I presented here, the base measurements, not the eddy-covariance measurements, but the base measurements are typically measured on a 1 to 5 minute interval. And then I'm calculating the Bowen ratio on a 30-minute interval. But then often for these comparisons, I'm definitely comparing a 30-minute flux to a 30-minute Bowen ratio, or I'm comparing a 30-minute flux that's been convolved to get to a 3-hour running average. And I'll do the same thing with the Bowen ratio. It diminishes the noisiness. It diminishes, you lose some fidelity in the data by doing that convolution. But you also take out things like hysteresis when you're comparing these time series. So those are kind of the approaches I've been taking to see if the method is robust. And yeah.
Any questions from the audience or online? Another M cubed.
I'm curious, have you thought about any larger scale parameters that might affect it? For instance, boundary layer height. Is that a parameter worth weaving into your neural network if you had it?
Yeah, it absolutely is. And it's definitely true for all the footprint work. So, I'm using a really simple parameterization for the mixing layer and boundary layer heights based on previous simple models for both stable and unstable conditions. But I'm only able to get away with that because I'm taking my measurements for footprints so near the ground. If I was even on a 10-meter tower, I think there would be too much sensitivity in those footprint models because of the exchange as you move up in the air column. I think there's always, I had a vineyard manager really want me to work on modeling frost prediction. And he had come to a practice of like, he would look at the buoy, the pressures on, because this is out on the coast, he would look at the pressure on the buoys and the air pressure on the buoys. And then he would say, well, you know, when these two are dipped below the other ones, then I'm going to get a frost. And he would turn his frost protection on. Their frost protection is quite expensive to run. So he was really invested in this. And he's like, I really would like you to give me a sensor-based model so that I can look at the parameters here. You know, there's some amount of precipitable water above us, and there's some amount of, you know, energy exchange that's happening during those daily transitions. Certainly we can come up with a sensor that's going to predict if frost is going to happen in some number of hours. And I do think the boundary layer height would be really helpful for those kinds of specific predictor, if you're looking at prediction. The microscale stuff, you know, the micrometeorology and those boundary layer synoptic scale things, they are coupled, but I mean, so many of those small scale forcings are affected by things that just change so much. If an irrigator comes and applies water, that changes the entire energy dynamics near the surface. I mean, they know that. They protect from frost and heat by spraying water or spraying chemicals or, you know, even burning soot pots. Like those kinds of, you know, big changes can be affected by, you know, seemingly relatively minor environmental variables and not so much by those controlling variables. Conversely, you know, if a big front comes in, there's nothing you can do. You're going to get frost at your site. So I do think so, but only for very specific predictive models would be my guess.
Any other questions?
I'll ask a dumb follow-up question, which is, I mean, because this comes up a lot with remote sensing data is, you know, predictors of boundary layer height or estimation of boundary layer height. What do you guys actually mean when you say that? Because I think there's more than one definition being thrown around.
Yeah, I mean, I even used two terms to answer the question. I talked about mixing layer, you know, and the boundary layer. I'm going to defer a little bit because I'm a micrometeorologist, and we've done some work. Like we did a study where we took a fiber optic, distributed temperature sensing fiber optic, and pulled it up with a drone, and then looked at the diurnal, or the morning and night transitions, and to look at the development of that boundary layer. So I mean, there's very simple descriptors, very simple, you know, not predictive, but descriptors in a number of texts where people talk about, well, what is the forcing behind the development of the boundary layer on that diurnal cycle? We know it goes up during the day when there's convection, and then it collapses again at night. I think, I mean, this is another one where I would reference authors who have thought about this more than I, about what are all the different forces that are at play. And part of the reason when we think about atmospheric boundary layers that I don't feel terribly well informed is that as you go to different scales, you know, at some point, other forces take control. And so when you describe a boundary layer height, whether that's, you know, a ceiling because of visibility or whether it's because of where water is precipitating out because of a change of potential temperature, I mean, those are all describing different kind of mechanisms that are operating simultaneously. And I think it's good to break those down by cases, but rather than just refer to a boundary layer as referring to just one thing. So I think more about stability than boundary layer height.
Jason, thanks. I'm still struggling with just the aridity versus energy balance closure. And I would naively think that if you measure all four terms of the energy balance properly, that it shouldn't matter whether the plant isn't being 100% productive, whether there is enough water.
Yeah.
Have you thought about what physically is going on to give you a lower energy budget? Is it an error in?
I'm listening.
That you're not that you're not getting, I don't know, enough G measured, or?
Yeah, so G is a huge piece of what I think is going on. I'm trying to go, I have some slides that I took out that I want to, there's one in particular I wanted to show because oh gosh, I hope I still left it in here. I think I just hit it. Sorry for the delay.
No problem.
Where is that box plot? Oh, here it is. Okay, so All right, so, okay, so this is that same kind of diurnal residual by hour, but for 3 different cases. So on the bottom, we have the fallow, which doesn't have a lot of variation over the course of the day, but there is a trend. And these represent hundreds, and I think in most midday cases, thousands of half-hour periods. And then the top 2 are in the same, they're both in irrigated plots. So this is from that alfalfa fallow trial. And I have 2 different soil heat flux plates with thermocouples measuring and measuring with radiant, using IRTs to get surface temperature and wetness sensors and a bunch of other things. So essentially what we have here are 3 cases. We have a case where there's no water on the bottom. On the top, we have irrigation, but with canopy cover. And then in the middle plot, what we have is irrigation, but no canopy cover. So it's in a row between the 2 crops, and it gets full sun. So we've got, the water is definitely affecting the modality of this, the water storage in the soil. That's, so it could be as simple as that my model for the thermal conductivity of the soil is insufficient to really describe how much soil heat flux is occurring. It could be texture, my textural characterization is incorrect, so I don't know what the bulk density is. And so, there are a whole bunch of specific techniques that may be insufficient to get a good estimate of the soil heat flux. And I'm focusing on soil heat flux here because all 3 of these plots are essentially using the same turbulent flux and the same net radiation, the same downwelling radiation measurements. And I have looked at especially upwelling long wave, so emitted long wave from the surface as another factor. But long wave emitted from the surface is function of temperature, of the surface temperature, and so is the soil heat storage is a function of the temperature, or maybe vice versa. And so, basically it's like, okay, well, we've got these different forcings going on, and we also have different characteristics of the system that are varying in time. And so the idea of identifying these modal behaviors is one where I'm saying, okay, these modal behaviors, it's not just noise of the sensors. It's not measurement error. If you have a mode, then there's a physical mechanism either in the sensor or in the true environmental variability that's tied to something that's happening in time. And I think, so to kind of answer your question a little more directly, I think that there's something wrong about how these methods, how a calorimetric method parameterizes heat storage in the near surface. I mean, it's an approximation. Is there a bias in it? I don't know. I do know that just in the surface above the surface, in the air above the surface, in the profile below the surface, that soil conditions change dramatically in the first few centimeters, and then that change is much less dramatic the deeper you go. So I'm curious if measuring soil heat flux as a gradient rather than across a plate with a thermopile would be a better starting point. And I'm making some sensors that allow soil heat flux to be measured over different averaging depths to get a better approximation of damping depth. There's that. There's also the amount of water that's stored in the crop above, and there's changes in albedo, and all of those things. It seems like you should be able to calculate all of those. And it seems like when we calculate to a surface flux, that they should all line up in any time period. The source term, as long as our footprints aren't mismatched terribly. If you've got energy coming in from the sun and energy being stored in the surface and in the soil profile, and you've got the turbulent flux and the latent flux that are well coupled with the surface, in any time period, they should match up. But what I'm seeing is that there is this lag, these lags seem to be related to the heat capacity as a function of the water content. It doesn't matter if it's in the soil or in the crop. It seems to be, a storage term. And that's what I think is going on. Yeah. Yeah.
Well, we are past our seminar hour, so let's thank our speaker for a great presentation.
Thanks, everybody.